I think.
Yeah.
But it's
But
fine. It's fine, sir.
if I turn off my fan, I will be like.
Okay, sir. No problem. It's completely fine. You are audible
Too
now.
hot in Chennai, you know.
Yeah,
Background
Yeah,
right, right.
noises.
too much hot.
Yeah. So bear with me. I will try to increase my voice after the session starts. Okay. Keep
Yes,
your volume at high. Okay. We are live now. So let me share
yes,
my screen first. Okay. So in week 11, the first lecture discussed about longest path, how to find the longest path in any given graph. Predominantly, the graph should be DAG. So once if you have a directed acyclic graph, we can be able to find the longest path inside that graph. So after that, we have discussed transitive closure, matrix multiplication, what is matrix multiplication and everything. And after that, we have seen how to find the shortest path from one vertex, one fixed vertex to every other vertex, or from any vertex to every other vertex. So depending upon the problem statement, so we just look at the problem statement. So look at what they are asking. So depending upon that, we used to pick our algorithm, and we use that algorithm to find the solution of that particular problem. So for those kind of things, so for in short, for finding the shortest paths in graph, we use Dijkstra algorithm, Bellman-Ford algorithm, Floyd-Warshall algorithm. So yeah, there are some conditions and restrictions where we can use only one particular algorithm and we cannot use the other. And there are few on few graphs we can use all the algorithms. So we'll look into that. Most probably I will cover till Floyd-Warshall algorithm. If there is time, I will take up this MCST, which is minimum cost spanning tree. Okay, and we will discuss prims and crystals. Okay, let us start now. Okay, before that,
these
yeah.
prims and crystals also little confusion.
Which one?
Last two, prims
Prims
and
and
crystals.
crystals. Okay, yeah, these three algorithms we use for finding
Shortest path.
shortest path. Okay, and these two algorithms are used to find the MCSTs, which are minimum cost spanning trees. Okay, so yeah, if there is time, we will cover this prims and crystals also. Anyway, in the solve with us, we will more emphasize on Dijkstra, prims and crystals. So even though if you miss it today, we will be covering these three topics again on solve with us session.
So these three algorithms are important.
Not like only these three. Even Bellman-Ford is also important. Try to understand Floyd-Warshall. We will not be going in depth of Floyd-Warshall as far as this course concerned.
Hey, it's time consuming. It's a
Yeah.
bigger,
So that is
longest
one.
algorithm.
See,
Yeah.
that is where that is why Dijkstra algorithm came into play. Time complexity of Dijkstra algorithm is very less when compared to Floyd-Warshall and Bellman-Ford.
Yes, yes, yes.
Right. And
Okay.
the negative side of Dijkstra is we can use it for only few graphs.
If
Yeah, we will
time
see pros
permits,
and
it's
cons.
good to go through last two algorithms also.
Yeah. If time permits, I will go through prims and crystals.
Okay.
Okay.
Thank you.
Okay. Yeah. Let us go back slightly back to week 10, where we require this DAGs again. So let me define what a DAG is. So from the name itself, we can see the graph should be a directed graph, a directed graph G, which contains some set of vertices and set of edges without any directed cycles. So if my directed graph doesn't contain any cycles inside it, that particular graph is called a DAG, which is directed acyclic graph. Now tell me, as you have passed through week 10, now tell me which one of the following is DAG, directed acyclic graph. So slightly complicated DAG, not very easy DAG. So you have to look at in deep and try to find any cycles present in
First
the
one
graph.
is not a DAG.
Second one have a cycle.
So some said this is not a DAG.
DE.
Second one has two cycles.
First is the DAG, right?
First is a DAX.
First is a death.
Yes, sir. First is a DAX. Second have cycle.
First is a DAG.
Yes, sir.
Some okay. This contains cycle.
Yes, sir.
Both are not dads.
Both are not DAGs. Okay.
No.
Sir,
That means
BDE
both
cycles.
contain cycles, is it?
Yes, both contain cycles.
Okay. Both are not DAGs is one answer. Let's solve the second one. So many of you are agreeing that this is not a DAG. So can I get one cycle to contradict this is not a DAG?
BDE
Sir,
BDE.
BDE.
BDE is a cycle.
So we got a cycle. We have seen a cycle here. B
DE.
E. Yeah. So this is a cycle. So we got a cycle. So this will not be a DAG. And also, yeah, there are many cycles inside this. B, DC, CE, and EV. Some big cycle. The thing is, even though you got one cycle inside a graph, that graph is not called as a DAG. So this is not a DAG. Sure. Now, now let us come to this.
How is DCE a cycle? How is
How?
DCE? How is DCE a cycle?
Not DCE. BD, BDCE.
BDCE. Okay, yeah, BDCE. Thank
Yeah,
you.
that is some big cycle.
Okay.
But the thing is, even if you found one cycle inside any graph, that particular graph cannot be called as a directed acyclic graph.
Yeah.
Cool. Okay. Now tell me. Now give me one cycle inside this graph to find
20
4, 3.
204. 04.
204. Is 204?
Sorry. No, sorry.
No, sir.
DAG.
No.
There is no cycle.
No
DAG.
cycles,
No,
sir.
sorry. No cycles.
It's a DAG, sir.
Correct.
It's a DAG.
So this is a DAG. Okay. The thing is, once I am asking this question, some of you said it is a DAG and some said it is not a DAG, and it will always be difficult to find a cycle inside any graph. Now that it is only 5 vertices and very few edges, you will be able to figure out by looking at the edges of it. But how we conclude in general, if there is a 10 vertices graph with some 30 edges inside it, so how do you check for a cycle?
We can actually do that programmatically, using BFS or DFS, and then list the vertices and mark the vertices as visited. And if you come across any visited again, then in the subsequent list, then probably we can do that, right?
More or less from DFS, we will be able to find the
Yes, sir.
tags.
Yes.
So if there is a
Backward edges.
then that means there is a cycle inside your graph, and that is one way of finding. There is another way of finding whether a given graph is a DAG or not. So you try to find a topological sequence by finding the integers of all the vertices inside your DAG. If you can able to come up with a topological sequence, then that is a DAG. If you are unable to come up with a topological sequence, then that is not a DAG. So this is another way of finding a DAG. Okay, you compute all the integers. So the facts about DAGs will be much more useful. If you know the facts about DAGs, using these facts, you can actually find whether the given graph is a DAG or not. So DAG shouldn't contain cycles. How we compute whether there is a cycle or not? You should have an integrity, some vertex with integrity 0 and some vertex with out degree 0. So check whether, just find the integers and out degrees of the given graph. If there is no integrity, if there is no vertex with integrity 0, you straight away cancel out saying that it is not a DAG. Or if you are unable to find a vertex with out degree 0, even then we will conclude that is not a DAG. You see, in this case also, in the second case, if you compute the out degrees, so this is 1, this is 1, this out degree is 1, out degree of E is 1, out degree of D is 2. So you can see here, there is no vertex with out degree 0. So you can straight away conclude this is not a DAG. Even here you can compute in degrees and out degrees. So you will have an in degree, this is an in degree, this vertex will have an in degree 0, and there is another vertex which has out degree 0. This vertex 1, correct? So once you have this, now you try to find the topological sequence starting from 2. If you can able to find the topological sequence, then that is a DAG. If you are unable to find the topological sequence, then that is not a DAG. So you can do in this way also. So either you can use DFS if you are interested, if you know well how to draw the depth for search for a given graph, then you can proceed that. If you don't know also, just know the facts about DAGs, and these facts should be true for every DAG. Okay. Yeah, if it is a DAG, then topological sorting and longest path in that particular DAG can be sorted. So now you have seen how the topological sorting or topological sequence can be formed. Now let us find the longest path in the DAG.
Excuse me, sir.
Yeah.
Sir, I had a problem on activity question.
In
Do I
week
ask?
11 or 10?
With 10.
Which one is it?
Sir, it's 10.2 question. 10 question number 2.
Just a second. Let me open it. Okay, 10.2.
Question number 2.
Okay, a college conducts an online gaming tournament. Is it?
Are you sharing screen?
No, I'm not sharing. I'm just asking whether this is a question. Is this the question?
Which one, sir? A college, yeah. Sir, college conducts an online game.
This one.
Yeah.
Okay. Let me tell you one thing then. This question was very well detailedly discussed in discussion forum.
In the discussion forum.
Yeah. Okay, let me just give you an idea how this works.
Sir, if it is discount, then I've got to check that.
Okay, then check it. If you are still
But
unable
where-
to find, you start a thread newly. If it is way below, I guess it's has been 2 weeks, right? By now. So
Yes, sir, it
start-
is. I couldn't find it in the forum, in the dashboard. Here only the forum.
Okay.
Is that discussed in the live sessions?
No, it's not discussed in the live session. But let me give you a whole idea what the question is all about.
Okay, sir.
So it is saying that there are some 7 games to be conducted, right? And there are some time slots given to that each particular game. So this fortnight to be given, this game should be played, or this game should be conducted in between 10 a.m. to 11 a.m. And another game, Dota, is to be conducted from 10:30 to 11:30. Okay, these are the time slots for that particular game to be conducted. Now, in the question itself, they have given you what are nodes and what are edges. So that the games are represented as nodes. Now, how many nodes you have?
7.
7. And there is an edge between 2 nodes if there is a clash in timings of the corresponding game. So if there is a clash in the timings means, see, Fortnite and Dota has a clash in timings from 10:30 to 11. Correct?
Yeah.
So at 10:30 to 11, both games should be conducted. Even Fortnite runs at 10:30 to 11. Even Dota runs at 10:30 to 11 time. So this is what clash means. If there is an at one particular time, if there is 2 games, then that is the clash.
So there is one edge in this.
There will be an edge from Fortnite vertex to Dota vertex.
Yeah.
Okay. So this is how you have to draw the edges between all the 7 nodes.
But sir, I calculated one thing that there are 7 nodes. So with that logic I did that. But in all options, there are 7 nodes.
Okay, yeah, 7. There will be 7 nodes, right? So because there are 7 games, there will be 7 nodes. Now fix each node with one game. So just fix this particular vertex is for Fortnite, and this particular vertex is for Dota. This particular vertex is for Destiny. Like this, all the 7 you label all the 7 vertices with the names of the game.
Okay.
Okay. Now draw edges if the time slots are contradicting, or if they clash in the timings. Draw an edge between those two particular vertices. You try to draw all the edges. Now there will be an edge from Fortnite vertex to Dota vertex, as well as there will be an edge from Dota to Rocket League. You can see there.
Oh, I understood. I understood that.
Understood? Yeah, this
Yes,
is
sir.
how you have to draw the graph.
And sir, the above question,
Okay.
the answer is the answer is option number 2. But how did the B8 be an node?
B8, BA.
The correct answer is B1, B5, and B8.
Hmm.
So why B8?
B1, B5, B8. Yeah, see, even B9 should be covered, right? See, depending upon the question, we choose the vertices, okay? They said in a factory, there are 10 buildings representing different departments.
Mhm.
So the factory wants some of the buildings as emergency assembly points, such that any employee can reach an assembly point without having to go past another building. So that means if he is at B0 or B9, he should be able to reach to the emergency assembly point, which is B8. So he will be allowed to move on one particular edge is the question. Okay.
And sir, and the dash here means something
So
apart.
that is an small error. That is a latex error. Okay.
Okay, okay,
Slash flower bracket is nothing but bracket.
okay.
Yeah, you don't need to worry about it.
Yeah, sir.
Okay.
Thank you, sir.
Sir,
Okay.
can we go for graded assignment?
Of week 10.
Sir, yes, sir.
Okay,
Question number 8.
you will get the solution. Don't worry.
Okay, sir.
Okay. So after seeing the solution, if you have still doubts, just come back tomorrow and we will discuss. Okay.
So by today night and solution will
Yeah,
be
mostly you
uploaded.
will get by today night. Solutions of week 10 you will get by today.
I do have a doubt here. Like you suggested to draw a DFS to find out that how can we find out? Like I know how to draw DFS,
Okay.
but
So
don't know how
okay,
to.
once you
How can we say that?
okay. So the thing is, you should understand what back edges, cross edges.
Okay.
Okay, this means
So if there is a cross edges,
not cross, back.
okay,
If you
okay,
have
back
a
edge.
back edge, then that gives you that there is a cycle.
Okay, great.
Okay.
Thank you. Yeah.
Okay, so these are some facts about DAGs. Let's come back to week 11. So we try to find the longest path in a DAG. So in order to find longest path in a particular DAG, we follow these steps. So first and foremost thing is you compute the integers of every vertex I in the DAG. So first thing is we should compute integers. Same we compute for topological sorting also. We compute the integers of every vertex before we start, right? So the same thing here also, we compute integers of every vertex in the DAG. After computing that, now we initialize. I hope you all doing CT, so you know what is initialization means. So before the start of process, we initialize something. That means we start with something. So what we initialize is this particular longest path to. So this is a function basically. This longest path to of every vertex to 0. So there now we have two numbers, two different numbers. One is in degree for every vertex, and another is longest path to is some other number for every vertex. So for every vertex we have two numbers associated. So first number is first number is the in degree, and the second number we initialize it to 0 for every vertex. After initializing this, what we do is we find a vertex. Now this is a DAG, right? We can only find the longest paths in a DAG. Now as this is a DAG, we have a vertex, some vertex with in degree 0. Now find that particular vertex and remove it from the DAG. When I say remove it from the DAG, it means you have to remove the vertex U, and the edges that are incident to you. Okay, so when we say removing a vertex, that means we should remove that particular vertex as well as the edges that are incident to that particular vertex. After removing this particular vertex u, which has in degree 0, we update the in degrees. What we do is we update the in degrees for all the vertices that are adjacent to the vertex u. So we'll update the in degrees of those vertices which are adjacent to vertex u, and we updated the in degrees. Now we have to update this particular longest path 2 also, this particular number also. How we update is this particular longest path 2 of vertex I is max of longest path to I. That means before, already if there is some number associated to that particular vertex, longest path to I, or 1 plus longest path to u, whatever the vertex we removed, we add 1 to that particular longest path to u, and whichever is the maximum, we pick that. We pick that for the vertex I that are adjacent to vertex u. Now ultimately what we are doing is we are removing some vertex u, and we are worried about only the adjacent vertex of that u, adjacent vertices of that u. So we update the in degrees of the adjacent vertices of u, and also we update the longest path to of all the adjacent vertices. Okay, we repeat this process 3, 4, 5. So this is if we keep it on stepwise. Now if you wanted to see pictorial representation will give us much better idea. Now if I have given you a graph like this, so first and foremost thing is we have to find the in degrees of every vertex. So this is the process of longest path, how to find the longest path in the graph, in the DAG. So we should compute all the in degrees of every vertex in the given graph. So tell me, what is the in degree of vertex 0?
0.
In degree
One.
of
It's one.
One. Sir.
1.
what is the in degree of vertex
2.
2. 0.
0.
for
And
4?
2 for the 4 2.
4.
2.
2.
3 also got
3 also 2.
So this is blue color numbers are the in degrees of every vertex. Also we should associate one more number which is longest path to that particular vertex. So we initialize everything to 0. So every vertex, red number for every vertex will be 0. Now what we have to do is we have to identify the vertex which has in degree 0. So which vertex has in degree 0?
2. 2 has.
2. 2 has in degree 0. So what we do is we remove 2 as well as the edges which are incident to 2. So we remove these 2 and these 2 edges. So if we remove, so what we have to do is we should remove vertex 2, and what we have to do is, and we update in degrees of vertices 0 and 4. So you see 2, this particular 2 is adjacent to vertex 0 and vertex 4. Only these 2 vertices are adjacent to this particular vertex 2. So what we do is we remove that vertex 2 and we update the integers of the adjacent vertices of 2, which are 0 and 4. So we update integers of this and we update the longest path to 0 and the longest path to 4 as max of. So we consider the maximum value of either the longest path to 0 or 1 plus longest path to of 2. Okay. So before vertex, so 1 plus longest path to the removed vertex or the longest path to that particular vertex will be the updated one. So max of this will be the longest path to 0. The same goes to 4 also. So the same thing. Same thing. Except here it will be 4. Either the previously longest path to number or 1 plus longest path to the just now removed vertex. Whichever is the maximum, we will choose that particular thing. So now see, now in order to compute this, let us see. What is the longest path to 0 we have initially have? What is the red number we up to now we have?
0.
0.
0.
Is 0. So 1 plus longest path to 2 we have 0. So now we have max of 0 comma 1. So what is max of 0 comma 1? So which is the maximum
1.
value? 1.
1.
So now the updated longest path to 0 will be 1. So that means the red number of 0 will update from 0 to 1. Same here also, see, longest path to 4 is 0. Same thing, 1 plus longest
0.
path to 0 is 0. So max of 0 comma 1 will be 1. So you see, we have to update the integers of vertices 0 and 4, as well as we have to update the longest path to numbers of 0 and 4. So if we update, this is how it will be. You can see now. So 2 we removed. So this particular vertex 2 we removed with along with these edges. If you remove that, this is how the graph will be. Now we
So
have
can
to
you please mute all?
okay. So after removing, you see we have to update the integers of 0 and 4. Now you see the integer of 0 will become 0 because there are no incoming edges. We removed that particular edge. Now the blue number from 1 to it became 0. And the same thing for vertex 4 also. Initially the integer is 2. Now after updating, the integer became 1. Now you see the red numbers of 0 and 4. Initially they are 0, 0, but now it is 1 and 1. Now this is how it will update. Now we repeat the same process. Now this becomes a DAG. So now identify the vertex which has integer 0. Now which one has integer 0?
0.
0.
0.
Right? Now what we have to do is we have to remove this particular vertex 0 as well as these edges, these 3 edges. So we have to remove these 3 with this. So after removing that, what we have to do is we have to update integers of vertex 1, vertex 3, vertex 4. Because you see vertex 1, 4, 3 are adjacent to this particular vertex 0. As well as we have to update longest path to 1, longest path to 3, and longest path 4. So how we update max of longest path to 1, comma 1 plus longest path to whatever the vertex we remove. So longest path to
0.
0. So it's the same thing, max of. Okay. Only changes here it will be 3, here it will be 3, here it will be 4. So LP2 longest path, LP2 1 plus LP2 0, LP2 0. So what is the longest path to 0 we have now?
1.
The red number. So 1. So this particular thing will be 1. So this is 1 plus 1. And what is the longest path to 1 we have? This is the
0.
red number.
0.
0. So this is 0. This is 1 plus 1, which is 2. Now what will be the max of 0 plus 2?
2.
What is max of 0? Sorry, what is max of 0 comma 2? So you have to choose the maximum value. So it will be 2. So see, directly the jump from 0 to 2, longest path to 1 has jumped from 0 to 2. So we update the longest path to 1. This particular red number of vertex 1 as 2 from 0. Right? Similarly, longest path to 3. Longest path to 3 we have 0. This is 0 or 1 plus 1, which is 2. The same thing again, 0 comma 2, which is 2. Now see here, longest path to 4. What is the value of longest path to 4?
1.
So you look at the red number. So it is 1. Now this is 1 plus 1. So what is max of
2.
1 comma 2?
2.
2. So this will be 2. This will be 2. All the red numbers are updated now. Now update the in degrees also. So in degree of 4 will be here. After removing 0, vertex
0.
0, what is the in degree of 4?
0, sir.
3.
1.
1.
1.
1.
Right. So now again you get a DAG. So again follow the same process. So what we have to do? We have to remove vertex
4.
4 and also the vertex 4 along with the edges which are incident to it. So after removing this, we get this particular graph. So what we have to do after that? You update the in degrees of
3.
3. In
3.
degree of 3 will be 0. In degree of 1 will be 1 only. Now what we have to do? We have to update the red values also. Red value of 1 will not
3.
change. You no need to worry about this one. Now we have to update only the longest path to 3. Which this is max of either long LP to 3 or 1 plus LP to 4. So this is the vertex we remove. Now if you see that LP3 is, so this is max of LP3 we have is 2.
2.
So look at this graph. LP2 is LP3 is 2, comma 1 plus what is LP4? Longest
2.
path to 4 is 2. So what is max of
3.
2 comma 3? This is 3. So this is how it will update. This will update to 3. Now again we reach to the final step.
Sir, why we choose max?
Because we are trying to find the longest path, not the shortest path. Longest one. Okay. We need the maximum value. Maximum farthest path we need. Okay, you can see here we are trying to find the longest path. I will explain you how we approach what is exactly the longest path in that particular path. So we choose max because see this particular longest path to denotes me that in order to reach to this particular vertex 3, I should take 2 edges. That is what this particular number said previously. But after updating, this particular number 3 denotes me that in order to reach this particular vertex 3, I can actually travel from one vertex and I can travel through 3 edges and I can reach to 3. So 3 edges is longer and longest than the 2 edges. Okay, that is why we take maximum. So this particular number, longest path 2 tells me that from particular vertex to this particular vertex 3, I can actually reach via 3 edges. So that is why this is became 3. Now what we have to do is we have to remove vertex 3 and update the longest path to of vertex 1 and the integrity of vertex 1. We will get 4
Longest
as
path is 4.
4 and this will be 0. So finally what we got is
Sir, are we also keeping a record like we were doing in the topological sorting of the
we will
sequence
keep
in which we remove the vertices?
correct. We will keep. See, the next example is a longer, big example, and we will keep the order. Okay.
That would be the topological sequence only. It's called the topological sequence or something else.
It is topological sequence only. At the above one, we write the this sequence which we remove in order we remove the vertices. So
Yes.
the order in which we remove the vertices is the topological sequence, and these particular red values at the final red values will be the longest path.
So each of these vertices.
Each of the vertices red number. So I have given colors to two different numbers, right?
Yeah. So to each of these vertices, we can find the longest path, not just to a particular vertex.
Yeah, that is what this tells, right? So the number finally we get the red numbers actually tells you that in this given graph you can reach this particular vertex from any vertex at maximum of 2 edges kind of thing if the number is 2. So the final values will be like this. Finest longest path values will be like this. So for 2 it will be 0. For 1 it is, so you can see for 1 it is 1.
1.
For 2 for 4, for vertex 4 it is 2.
2.
For vertex 3 it is 3. For vertex 1 it is 4. So finally these particular red numbers you see, now you see the largest number I have is 4. That means in this particular graph there is a path which has length 4 from one vertex to this vertex 1. So that path is basically this. So this is the longest path in this particular graph. So you can reach from vertex 2 to vertex 1 via 4 edges from 2 to 0, 0 to 4, 4 to 3 and 3 to 1. And this will be the longest path, not the shortest path. Shortest path would be different. Shortest path would be something like 2 to 0 and 0 to 1. So this is the shortest path from reaching from 2 to 1. Okay, so this shortest path is different from this longest path. This longest path gives us from one vertex to another vertex how many maximum number of edges I can travel in between. So this is the longest path. So if you follow this method, this will give us the longest path to every other vertex. You can see here also this particular number 3 tells me that wherever vertex I start, either it is 0, 1, 2, 4, I can actually reach 3 with less than or equal to 3 edges. I cannot use four different edges to reach particular vertex 3. So this is what this tells me. So I can maximum use 3 edges. So that is also from this vertex. So from 2 to 0, 0 to 4, 4 to 3 is the longest path to vertex 3 in the given graph. So this is the longest path. So from 0 I can directly reach to 3 directly with one edge, or I can maximum use from 0 to 4, 4 to 3. So 2 edges.
I
From
have
1
a
I
doubt
can.
here.
Hmm.
This longest path tells only to the vertex. From it won't tell anything about from where.
From where you have to backtrace it. That's it. So this is 4 comes before after 3, right? You have to backtrace it. You can
But
backtrace
here,
it.
but for while executing, we are not bothered about from where. We are only looking for 2.
Yeah, we are worried about 2.
Okay.
And also we are not worried about all paths. We are worried about the longest path in the graph.
But from where it's starting, where it's coming, we don't need to know.
That we will know. That is direct from DAX. Actually, it starts from the in degree 0 vertex.
Okay.
So whichever the vertex has first graph, whichever the vertex has in degree 0, that is the, from there only we get the longest path.
So can I say from the first step, it's the distance from longest path 0 to 4, as we started from the vertex 0?
We started from vertex 2, right?
Oh, sorry. Sorry, 2 to 4. That's it only, right?
See, that is what 2 to 4 is the shortest path. So using this direct edge, I can reach 4.
That's the shortest.
Okay. But that is shortest. The longest will be 2 to 0, 0 to 4. That is why this number is 2. So you can use 2 edges maximum. Maximum you can use 2 edges to reach 4 from this vertex 2. Okay. Via 2 to 0 and 0 to 4. Also you can go from 2 to 4. But which one is the longest? Which one is the longest one? 2 to 4 is longest, or 2 to 0, 0 to 4 is longest?
2 to 0, 0 to 4.
Yeah, that has more number of edges. In terms of edges, we talk the longest path. So this gives us the longest path. This particular number tells us from the vertex which has in degree 0, I can use maximum of 2 edges to reach this particular vertex 4. Maximum of 3 edges to reach vertex 3. Maximum of 4 edges to reach vertex 4. Okay. So this gives us the longest path. So don't forget, don't go for minimum. So that is why we go for maximum. So this particular term, why we go for maximum is, this is longest path to 0. Before that, I am using 0 edges. After I am using 1 edge. So if I have to choose the longest one, I should go for the maximum one. If I want to find the minimum shortest path or the shortest path, then I will go for minimum. Okay, so don't forget about this. So this is a smaller example. Let's take a big complicated one. For us, this is complicated. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 vertices with us. Now we have to find the longest path in this particular DAG. So every time drawing this graph will not be possible, right? So as there are only 5 vertices, you can draw this, and this. Done. What if there are 10 edges like this, 10 vertices like this? So what we have to do is the same process we repeat. So first check whether this given graph is DAG or not. Anyway, I have given this as a DAG. So just find the in degrees of every vertex. So in degree of D will be 0, D will be 1, I will be
1,
1,
2, 2,
2,
1,
1,
1,
1,
1,
2,
2,
4.
4.
So we have computed in degrees. Also you compute this you initialize this longest path to as 0, 0. Everything to 0.
So, I have a question. So you said that there are conditions for that in degree is 0 and also the out degree is at to 0. One out for one vertex. And
You should have for one vertex out degree should be 0. So this particular G has out degree 0. Okay. Also you cannot find cycles inside this. While we solve this graph, if I am able to find the longest path and topological sequence, then automatically it implies that this is a DAG. Okay. Yeah. Now from where we should start?
B.
B. Correct. So what we do is we note down that particular vertex in this topological sequence B, and we will remove B as well as
Edges.
the edges which are incident to the particular
It's
vertex
not
B.
visible. Can you please zoom out little? Full page is not visible.
It is visible.
Okay. Now it's
Okay.
Yeah.
Yeah.
So we removed B along with those three incident edges. Now after removing, what we do is we update the integers. Now see what will be the integer of E. Usually it will decrease by 1. So if it is 2,
Yes.
it will decrease by 1.
1.
Now this becomes 1. If it is 1, it will decrease by 1.
0.
0.
0.
0.
Now see, previously we have never encountered this case. So at the same time, two vertices having integers 0. If you approach to this particular situation, then you can use any one of the vertex. If it
Sir,
is not, yeah.
if the two incoming edges to a particular node to a different nodes is there, so both the cases it will be implemented, or only one case will be implemented, the other one will not.
Can you ask me again, please?
Now D is from D there are two indices to I. Now if I want to eliminate I, both numbers will change or only one number will get changed?
Both numbers will change. So see here itself we removed B. We updated only integers. We have to update this particular red numbers also. So what will be the red numbers? It will be max of 0, 1 plus 0. So all these three will have max of longest path to this particular I or 1 plus longest path to B. So longest path to I is anyway 0. All the red numbers of D, C, E are 0. So it will be 0. 1 plus longest path to B is also 0. So for every, I'm computing directly, okay. So here I can take the vertex D, C, E, anything. So for any value, it will be 0, 1 plus 0, max of 0, 1 plus 0, which will be 0, 1, which will be 1. Now the red number need to be updated to 1 for every vertex C, D, E. Okay. So you add this B, you make the longest path to B to 0. Now here the red numbers for E, C and D become 1. Now we have vertex C as well as vertex C, vertex D with integers 0. You can remove any one of it if anything is not given in the question. So in question, if it is given like you should follow the alphabetical order, or if the vertices are labeled with numbers, you should follow the numerical order. Unless we mention that, you can remove any C or D. So let me impose one more condition also in this. I say follow alphabetical order. Vertical order while you remove the vertices. Yeah.
If in the question, if there is no alphabetical order not given, then we compute both of them. First we take D or other.
See, that is one possible topological sequence. While you remove D, that is one possible topological sequence. While you remove C, that will be another topological sequence possible. So you can have more than one topological sequence.
Yes, sir.
Okay. Yeah. So usually we will mention. So if
Sir,
there are
I could
many,
not understand. We have taken E. I have missed this point. How did we get D, C, and E?
see, because what we have to do is we have to
Once we
find
remove B.
B, we have to update the integers and the longest path to of the vertices which are adjacent to B.
Okay, I got it.
Okay. Now the E, C, D are adjacent to B, so we have to update the integers. That means the blue number as well as the red number of E, C, D. Okay. So that is what we did. So that is what we did. We updated in degrees as well as the longest path to of vertex C, D, and E. Now the next step is we have to remove this particular
The
vertex.
longest path, can you just repeat once? Because the in degree I understood that whatever number, but the longest
Longest
path
path
initial.
to longest
Yeah.
path to the vertex C will be max of longest path to the vertex C or 1 plus longest path to B. So that is what we did in the above also, right? So in order to update longest path to 0, which is the adjacent of 2, either we took longest path to 0 or 1 plus longest path to the vertex which we removed. So vertex 2 is removed and 1 plus longest path 2. Okay, we choose the max of this, and that will be updated as longest path to 0, which is the neighbor or adjacent to the vertex which we removed. So even here also the vertex which we removed is B, and E, C, D are adjacent to B. So we update the longest path to C, D, and E as the longest path to C as max of longest path to C, or that means previously the previous value, or the 1 plus the longest path of the vertex which we removed just now. So the longest path of the vertex B is 0. So the red number of B is 0. You can see here also. So the longest path to B is 0. So 1 plus longest path to B will be 1. And the longest path to C previously we have is 0. So max of 0 comma 1, now it will become 1. So that means longest path to C will be updated from 0 to 1. Initially it is 0 here. That is what we initialized, everything to 0. Now it is updated to 1. The red number updated to 1. Similarly for D and E also. So it just here changes D and D and E and D. Nothing changes. So these all values will be same. It will be turn out to be 1 again. So simply to say, if you are removing, so this is one what we say, some ratta type of thing. If you are removing one vertex which has in degree 0, then the adjacent vertices ka in degrees will reduce by 1, and the longest paths will increase by 1, or it will not change. Got the point?
Can you please repeat it once again?
Simply, so initially if you have 2 here, let's suppose, I'm just supposing, if you have 2 here, if you are removing one vertex along with that along with the edges, the in degrees of the adjacent vertices will decrease by 1, and the longest path 2 will either increase by 1 or it will not increase, it will remain same. So here you see the longest path to B is 0, so it will either increase to either E, C, D will increase, update to 1, or if the previous itself is maximum, it will not update. So now you see the C thing has 2, the vertex C has longest path 2 has 2. So either it will be 1 or it will be 2, max of these 2. So max of 2 comma 1 will be 2, it will not change, but here it will change, it will increase by 1. That's it. In degree will decrease by 1, longest path 2 will either increase by 1 or it will not change. So that is one simple way you remember, but every time we forget these things. So follow standard approaches only. So yeah, understand how we write this, why we take max of previous red number we have, comma 1 plus longest path to the vertex just now we removed. So if you can able to understand this, then no need of remembering that. Now let's come back. Now next we have to remove vertex C. Correct? I said alphabetical order. So we have C and D to be removed, but in alphabetical order, C comes first. So we remove C as well as the edges which are incident to C. So we remove this as well as this. If I remove, after removing, what I have to do? I have to update the in degrees of which vertices?
E
A
H.
E
H.
Correct.
E and
H. So now I will add that particular vertex C to my topological sequence, and the longest path to C is 1. Okay. Now I have to update the integers of A, E, H, and also I have to update the longest path to of A, E, H. Now see. So in order to update, now we will have 0 or you see 1 plus 1.
2.
So max of this thing.
2.
So here,
2.
yeah, 2. That will be 2. So let me update the integers first. So this 1, and this 4 will reduce by 1 each. So this will become 0, 0, and 3. Correct?
Yes.
It will reduce by 1. Now the red number will change like this. Either it will be max of either the
1
previous
or
one,
2.
1, or 1 plus 1.
2.
2.
Here also it will be max of 0
0 and
or 1 plus 1.
1 plus
Right. Now what is the max of 0 gamma 1 plus 1? It will be 2.
2. 2.
This red number will happen. Even this is 2.
2. 2.
Right? So this is
2.
this has taken
This is 3.
2, 2, 2.
2.
Max of 0 comma 2.
Okay.
2
Okay, sir.
only.
Sorry.
Yeah, this will
A,
also be
E,
2.
H all are 3.
Now we will remove this. Now see, now we have vertex A in degree 0, vertex E in degree 0, vertex D in degree 0. So as we have to follow the alphabetical order, we have to remove vertex A.
A.
A as well as these two edges. So we can remove. Okay. So I remove. I will add this vertex A to my topological sequence, and the longest path to A will be 2.
So, like suppose for A, red number would be like 1, then we go for E, we remove E, right? For the longest path.
No,
No,
it
no,
is
no. You don't need to worry about the longest path number. So while you
Okay.
remove, just look at the integrity, that blue number only.
Okay.
Okay. Yeah. Now see. Now we have to update the integers of J and F. So those are the two edges, right? Those are the two adjacent vertices to A. So the integrity you reduce by 1. This will become 0. Integrity reduced by 1. This will become 1.
1.
Now the red number changes like this. So it will be max of either the previous one, which is 0, or
1 plus
1
2.
plus
1, 2 plus. Yeah.
3.
so it is 2. So here also it will be max of 1 plus 2 or 0.
0. Yeah.
So this will be 3. 0 comma 1 plus 2 will be 3. This will also be 3. So we are choosing the max. 3. We complete the removes.
Sir,
Now
F was 0 no before the longest path to F was 0, right?
Longest path to
It's
A.
2.
F
2, 2.
F longest path to F was 0 initially, right? And that
Initially it is 0.
0. Then
Now
comma
it
like
is
from A it was 2. Then 1 plus 2.
correct. So 1 plus
Okay.
2 is 3. Initially it is 0. Max of 0 comma 3. Now this is the updated longest path to for F. So max of 0 comma 3 will be 3.
Okay. Okay, sir.
Yeah. Now we proceed. Now we have to remove D. So alphabetical order, we have D. So remove this. So once we are removing that, we will add that to the topological sequence. And the longest path to D is 1.
1.
Correct? Yeah. So you see the red number 1. Now see. Now look at how this will update. So let us update in degrees first. So in degrees will reduce by 1. So 3 minus 1, this will be 2. And 1 minus 1 will be 0. Now coming to the red red values, red number. This will be initially it is 2.
2.
So this will be either max of 2 comma
2.
1 plus 1.
1 plus 1.
1 plus the vertex, longest path to the vertex which we know.
Yes, sir.
So this is max of 2
2
comma 2.
comma
2.
So what is max 2 comma
2.
2?
2 only,
Only.
sir.
So this is not updated. So
Yes, sir.
this remains same. Okay. So this tells me that either you follow the previous path or either you follow this path. The longest you can travel only with 2 edges. So it is not updated. So this is 2 only. Now what will be the value of this? Max of 0 comma 1 plus 1.
2.
So this will be
1
2.
plus 2.
1 plus
1 plus 2.
1 plus 1.
this one, this one.
0 plus 1.
1 plus 1.
Yes, sir.
So 1, 1. 1 plus 1, 2.
1 plus 1. Okay. So we are removing vertex D here. Vertex D longest path is only 1. The value of longest path 2 of D is 1. So 1 plus 1, this will be 2. So max of 0 comma 2 will be 2. Okay.
Yes,
Correct?
sir.
Yeah. So we remove D. Now. Now see, now we have again 3 vertices which are in degree 0. So all in while we are traveling or we are taking in alphabetical order. So we remove E. So we remove E and this particular edge. So once I remove E, I will add to the topological sequence. And the longest path to E is 2.
2.
And yeah. So once I remove this particular edge, so I have to update the integers of
H.
the vertex
H.
edge, which is 1. 2 minus 1. So integer will reduce by 1. Now what happens to the longest path? This will be
3.
max
3.
of
1
1
plus
plus previous
2.
one. 1
1
plus
plus 2.
2 comma
2.
already 2 is there,
3.
right? Max
Yeah.
of 3 comma 2.
3 is
3.
3. Max of 3 comma 2. 3. Correct. So the longest path to H now became 3. We remove E. Now we have I and J with us. So we have to remove I. Correct? So remove I.
yes, sir.
Add it to the topological sequence. Longest path to I is 2.
2.
So when I remove I, this particular edge will be removed along with that. Now if I am removing this particular edge, I have to update the integers of vertex G and the longest path to vertex G. So initially the integer is 2, so reduce
No,
by
1.
1. This will become 1. So what happens to the max? What happens to the longest path? Initially it is 0.
3.
This will be max of initial value is
0
0.
and 2 plus 1.
1
1
plus
plus 2.
1 plus
2.
2.
longest path to I.
2.
Is 2. So
3.
it will be max of 0 comma 3.
3.
So which will be 3. So this will be 3. We remove I. So this will be 3. So this is how we update the longest path to for every vertex. Now this became 3. Now we remove J. So we removing J, that means we remove J along with this edge. So add J to the topological sequence. Longest path to J will be 3. Now what happens to the integer of H? If you update, this will become 0. And the longest path to H will be
4.
max of already 3 before the value is 3 or 1 plus longest path
3.
to J, which is 3. So this will be max of 3 comma 4, which will be 4.
Oh, it will be 4, sir.
4. So you see how the longest path to H is being updated. So initially it is 2, after that it went to 3, after that now it is 4, right? So we remove J.
తమ్ముడున్నాడు కదా వర్షి తమ్ముడు నోట్లో ఏం పెట్టుకో నీకు.
Okay, we removed J. Now we have to remove H along with this particular edge. So after you remove H, the longest path to H is 4. Like this. Update the in degree of
0.
F. This will become 0. So what happens to this now?
5.
Longest path. So this will be max of
5.
either 3 or 1 plus previously removed 1. Previously removed 1 has longest path as 4. So 1 plus 4 is 5. Max of 3 comma 5 will be 5. So this will be 5. Cool. So we remove. So now we have to remove F. F and add F to the topological sequence. While you add F, the longest path to F is 5. So we remove this, and we update the in degree. This will become 0. And the longest path to G will be max of
6.
max of 3 or previously it is 3
1 plus
or
5
1
plus
plus 5.
1.
1. Yeah.
So this will be 6.
6.
So finally what we do is we remove G, we add G here, and the longest path to G is 6. So this particular number 6 tells us that in this particular graph which we have seen earlier, so this particular whole graph.
Sir, can you mute everyone, please?
Okay, just a second. Okay, so this 6 number tells me that in this particular graph we have a longest path that has length 6 from one vertex to another vertex. Usually that path will start from the vertex, the first vertex which we remove. So this is the longest path in this graph. So 0, you see, this is the longest path. So this is not the shortest path to reach from vertex B to G. This is the longest path that I can find from vertex B to vertex G. So in this particular graph there is no path which has length 7. So from any vertex to any vertex there is no path which has length 7. That is what this particular number 6 tells us. So this particular 6 number gives us there is a longest path from B to G, and that longest path length is 6. That means you can travel 6 edges in between. So this is the longest path.
Sir,
How did you draw this?
This longest path, in case let us say you began with B, and let us say I should, if I start with E, and will I also have the longest path to G will be the
No. See, this is how I traverse back the longest path. So from these numbers I travel back. You decrease 1, and you reach till 0. So the highest value 6 has is the longest path of the longest path to G is 6. So the red number of G is 6. So
No,
you
sir.
start from 6.
Sir, my question is, G is the longest path 6, I understand, and we started from B, right? Now let us say if I would have started from E, alphabet E, then would it also give the same longest path 6, or it will be less?
No,
It
right?
will differ.
Why will it give you the longest path 6? So now you are starting from E. So in this particular DAG, it tells that if you are starting from E, there is only one outward edge that will go to H, and from H there is only one outward edge that will go to F, and from F there is only one outward edge which goes to G. So the longest or the shortest from E to G you can reach is 3. The longest path or the shortest path will be 3, not 6. This particular number 6 gives you the longest path in the graph. Okay, considering all the vertices and all the edges.
How to draw this path, longest path?
Yeah. See, this longest path you can draw by taking the vertex which has the highest red number. So 6 is the highest
Yes.
number we have. So from 6 you traverse back to 5. So which has 5?
F.
So you go back to F. So from F you go back to 4.
H.
H. From 4 to 3.
J.
From 3 to 2. So from the graph you can see I can reach J only via A. So traverse back to A and back to C and back to B.
So can we go in reverse direction also?
This is how we can go. While you are coming from front, see, I can tell you one thing. When you are playing a mage, so you know mage games, right? There will be a start and there will be an exit, and in between there will be a series of doors you have to pass. Correct?
Yes.
So once you know all the paths, how you can, there can be many different paths you can reach to the exit, and some will be shortest and some will be longest, and some might not reach the destination also, right? After you have traveled through each and every path, now now you know when you are at end point, now you know how to go back to the start. Correct?
Yes, understood.
Yeah. So that is how you can traverse back. Either you traverse back or you start from the starting. See, I have drawn this because see in this longest path I have 0, 1, 2 and 3 for J. This longest path I have for J. Okay, so look at the path in which J comes, in which vertex, in which the vertex J comes. So that means J should come. You know, if J comes, A should come. If A comes, C should come. If C comes, B should come. This is how you can traverse back and
Yes, clear.
friend.
Yeah, clear. Thank you.
So this is what this number tells us. The longest. This is how we find the longest path to in a graph also.
And sir, one more thing, like any graph, like there will be only one longest path, right? Or
Yeah, only
one
longest path, or you can have multiple. See, the thing is here we have updated. The lastly we got something like max of 3, 6, but it may not be 3. It might be 6 also. You never know, right? Even there might be another path which has length 6. Also, you got a new path which has length 6. So here itself you may get or else you take this smaller one. So B to E. Let me give you an example, small example. So A, see this particular example. So the longest path from A to D is either A to C, C to D, or A to B, B to D. Correct?
Yes, sir.
Yes. You can have
so
more than one longest.
Multiple longest path can be possible.
Yeah, multiple longest path. Okay. Okay. Now that we have seen longest paths, let's move to transitive closure. So this particular transitive closure is also one important application in graph theory, where we actually where we actually use this transitive closure in order to find whether the given graph is connected or not. So if the graph is connected and if it is undirected, then if you find the transitive closure, it will become the complete graph. So there are few applications on this transitive closures. So what is this transitive closure of any graph? So if I have a graph G with me, how to find the transitive closure of that particular graph? So this is very simple actually. If you have a graph with you, so this is what you have to do. So if you have some graph G with me, Now what I have to do is I have to add edges. That's it. I have to add some edges to this particular graph G, so that the newly formed graph will be the transitive closure of the previous graph. So how we add edges? How we add the direct edge? So this is how we add. If there is a path from one vertex U to another vertex V, path. I'm stating path here. Okay. If there is a path from vertex U to vertex V, no need to be direct edge. If there is a path from vertex U to vertex V, then what we do is we add a direct edge from vertex U to vertex V. For all such UV belong to my vertex L. Okay, we have to choose those vertex U and those vertex V which has paths. So if there is a path, we add the direct edge. So after we finish adding all the direct edges, the newly formed graph, which can be denoted like this, G bar, G over bar, is called the transitive closure of the graph G. Okay, this is what the transitive closure. So this is basically called, in other words, this is called as reachability graph of the graph. So this is actually, yeah. So yeah, this is actually also called as reachability graph or transitive closure of previous graph. Transitive closure. See, now we have this graph G. So there is a directed graph given to us, which is of 5 vertices with some 6 edges. What we have to do is we have to take the whole graph and we try to add edges for those 2 vertices which has a path. Now see here, vertex 2 to vertex 4, there is a path. So 2 to 0, 0 to 4, there is a path, right? There is a path from 2 to 4. So now we have found 2 vertices which has a path. From vertex 2 to vertex 4, I have a path. So what I have to do is, I have to add an edge from this vertex 2 to vertex 4. Similarly, vertex 4 to vertex 1, I have a path from 4 to 3, 3 to 1. So what I have to do? I have to add an edge from 4 to 1. Okay. Are there any other pairs of vertices?
Sir, here the logic, like let us say you added 4 to 1, the direction could be different. No, 1 to 4 also could be connected, right?
No. See, that is what I said. The direction is important. If there is a path from vertex U to vertex V, so starting from U to V, then we add a direct edge from the vertex U to vertex V.
Okay, if it is from U to V, then okay.
This is just the reachability. So why I am adding this particular red edge between 4 and 1 is, it says that actually I can reach from 4 to 1. So that is what this tells me.
2 to 1.
Sir, actually, U to sir, here the concept of U to V, how could you please repeat this one? Let us say the red color is not there, 2 to 4, of the 4 to 1. How did you define 4 is U and 1 is V? Like how do we differentiate
because
that?
there is a path from 2 to vertex V.
No, that also
vertex
you
4.
made it right now, right? That also you made right now, right?
That is why we added an edge from 2 to vertex V, 4. So if you have a path from 2 to 4, then I add a direct edge from 2 to 4. So this particular red edge tells me that there is a path from 2 to vertex 4. So there is a path. There is a path 2004. So that is why I add an edge from 2 to 4. But there is no path from 4 to 2 if you observe. There is no path. So you can see here.
Okay.
There is no path from 4 to 2.
Sir, actually, you made it in the beginning 2 to 4. Then it directed you. Then we need to go for 4 to 1. Let us say if I would have started from 4 to 2, then from 2 to 1, will that be okay, or that will just not okay? If I would have started in the beginning, now that both the red colors are not present, I will start from 4, I will go to 2, then from 2 to 1.
So see, the thing is, if you are starting from 4 and if you are going to 2, that tells me that there is a path from 4 to vertex 2. Is there a path? Is there a path in the graph G from vertex 4 to vertex 2?
No, sir.
No, right?
Okay.
So here we are creating a edge to move directly.
Yeah, to move directly or reach
Directly.
reach directly.
To reach
So,
directly.
so that's it. So this is gives us reach ability. If there is an ability to reach from one vertex to other vertex, then we add a direct edge from that vertex to that particular vertex. So this particular vertex 2 has the ability to reach to 4 via these two edges. That is why we say this from vertex 2, vertex 4 is reachable. That is where this term reachability comes. Reachability. If I am able to reach to that particular vertex, then there is a path from vertex 2 to vertex 4. If there is a path from vertex 2 to vertex 4, then I draw a direct edge from vertex 2 to vertex 4. That's it.
Can we draw an edge from 2 to 3 also?
Yeah, we should add. See, you see, there is a path from 2 to 3, right? From 2 to 3, there is a path. So therefore, we should add an edge from 2 to 3. Direct edge from 2 to 3. Similarly, from 2 to 1 also there is a path. So I can, there is a reachability from 2 to 1. So 2 to 0, 0 to 1. So I should add a direct edge from 2 to 1. So I guess we can add only these 4. Correct? Yeah, correct. Yeah, correct. So this particular graph becomes the transitive closure, including these red edges. This particular graph becomes the transitive closure of this particular graph G. So this is the transitive closure of this graph G. Okay. Yeah. So now questions can be like this. Now we won't give you a simple 5 or 4 like this. Questions can be like this. How many edges will be there in the transitive closure of the below given graph? So we are asking number of edges in the transitive closure of the below graph, not this particular graph. You have to find the transitive closure of this graph. Once you find the transitive closure of this graph, then in that particular graph, how many edges are there? That is the question. So what you have to do? We have to add edges, correct?
Yes.
Am I audible? Yeah.
Yes.
So you have to find the reachability graph, which is the transitive closure graph. So you can start from any vertex. So let me start from vertex B. So from vertex B, I can reach D. Also, there is a direct edge from B to D.
Sir,
From
we can
vertex
do it.
B,
We can do it in any graph, or it should be direct.
no. You can do it in any graph. So from vertex B to vertex I can reach. So I should add a direct edge from B to I. Correct. Now from vertex B to H also I can reach. So I should add a direct edge
B to H.
from B to I. So similarly B to A I can reach. I should add an edge from B to A. Correct. Similarly B to J, B to F, B to G, all these vertices I can reach. Okay. So I hope I have not forgotten anything with respect to B. Okay, once you are done with B, just move to the other vertex. From D, I can reach I. Also, there is a direct edge from D to I. From D, I can reach to G. So there should be a direct edge from D to G. Similarly, from D to F I can reach. So there should be a direct edge from D to H. See, D
So
to
we can
H.
draw outward edges also.
Those are just a drawing. Those are not outward or inward. Okay, I can draw from inside also, but it will look much more complicated. So
Yeah, it's okay. It's okay.
So yeah, so D to F. Yeah, I guess we are done with D because I cannot able to reach to E, or I cannot reach C, or I cannot reach A, I cannot reach J. So once I am done there, I will move to the next vertex.
Sir, here also you can join D to C, no? Or what exactly is preventing us not to join the D to C?
D to C. Actually, the thing is you cannot reach from D to C. So there is no path from D to C.
So because you connected D to F because there is a way D to H and H to H. That is why you connected D to F.
Yeah, correct.
Okay.
So that is why we added a direct edge from D to F. So I cannot add direct edge from D to C because there is no path, there is no way to reach C from D. So
but I can make transitive closure, no? So transitive closure is only this defined if it is connected through other some intermediate nodes, then only I can make a direct connection.
Then only you can make a direct connection. After making the direct connections, once you are done with every vertex, once you are done with adding all these edges, then that particular graph will become the.
Sir, can you write down the matrix form for this? Can you write this down in the matrix form instead?
Matrix form is little complicated to draw. See, there you have to see, there you have to understand. See, I have matrix multiplication later. So
okay, sir.
Actually,
So here we will count not only the existing edges but also the red ones that you have put, right?
Yeah, correct.
Okay.
Correct.
So we are calculating one-step graph, like in. So this was then computational thinking also.
This is one-step graph. Huh?
Yeah, one hop.
One hop and hops.
This is okay. That means you can reach.
We can reach G from D in one hop, like that. It was.
One vertex in
We had something like that there.
Okay. Yeah, not only one hop, right? See, in hop terms, B to G also I drew the direct edge.
Many hops.
Many
hops. Yeah. Not
So
only
yeah, all possible.
all
Okay,
possible paths. So that is what all possible ways or paths. If there is a path, we will add a direct edge.
But the bigger the graph gets, more complex it gets.
Bigger the graph. See, until 10 vertices, not even 10. In graph theory, till 15 vertices, it is smaller graph. 1-5. Okay.
Okay.
So yeah, so I got the point, but so anyway, we treat these graphs are very small. Okay. So
You treat it as small, but for us, it's very big. For the students, it's big.
Yeah. Even for me, it's big. But when it comes to the graph theory, whole graph theory, in present situation, where we stand is, even the 15 vertices graph is a smaller graph. Okay.
How long
But
will it
everything
take to
is
solve it in the?
computerized nowadays. Are we drawing with pen and pencil or paper? Everything is computerized. Many algorithms.
Yeah,
Everything is
see, that is the
computerized.
difference between pen and paper and the matrix form of the computing the transitive closure. That is the difference. So now I am just drawing on the paper. So
Will it be asked in the exam? This one?
Not particularly. You don't need to worry about big graphs. I already mentioned we will not go beyond 9 vertices, 7 vertices. Okay. And 10 is the maximum value for us also. Even creating question is much more difficult than solving it. I hope you understand. So if we had taken some 15 vertices, then we will make, there is a chance of making error. more array.
Yeah, it
And less
happens.
Yes, sir.
number of vertices, then there will be less chance of making it. Okay,
But
anyway.
one thing in exam again, actually students has to note down this graph and the paper, and again we need to color. So it consumes a lot of time actually.
Yeah. See, we understand. We understand. No need to worry about how the questions will be. Questions will be much more easier than quiz 1 and quiz 2. Okay. Okay, I'm just explaining this visually. That's it. So if I talk in machine languages, I should bring this adjacency matrix, and I have to compute a square to get the paths of length 2 and a cube, which are path of length 3. Likewise, and if I have, okay, I will explain that thing also. So you have to do this thing. You have to add all the edges, all the red edges. Once you are done, you just count how many number of black plus red edges are there in this graph, and that is the answer for our question. And if we not able to draw this pen and paper, if we don't have that much space or that much visual uh, skills, if you don't have that, what we have to do is we have to find the adjacency matrix first. So if you have the adjacency matrix, you should compute a square, which gives me the paths of length 2. Okay, so how we compute that I will tell within a minute, but understand, follow me. So you have to compute the adjacency matrix, which is actually gives me the paths of length 1.
Yes.
Okay, now you have to compute a square. I will tell you how to compute a square from a. Actually, you can compute a square from a, and a square will give you the paths of length 2. Similarly, a cube will give you paths of length 3. Likewise, you compute a to the power n minus 1. So these are paths of length n minus 1, lengths n minus 1. So what you have to do is, if you wanted to compute the transitive closure, which is a plus or something, I will give I comma j. So this is the ith row jth entry. So in my transitive closure, ith row jth entry, I will give 1 if a or a square or a cube. So any one of this becomes 1, I will give 1 to my transitive closure. Understand? So a I j is 1, or a square I j is 1, or so and so on, or a to the power n minus 1 I j is 1. So any one satisfies, I will give 1, or else 0 otherwise. So this is how we compute the transitive closure. So in order to compute this, you have to compute. So if the graph is of 10 vertices, you have to compute a to the power 9. Okay.
It's also a lengthy procedure.
Yeah, it is also a lengthy procedure, but you can do it in computer. So this method can be done in computer.
Okay.
So once you have adjacency matrix, just queue that adjacency matrix to the computer, and it will compute the a square, a cube, and everything. Just write the code write this code.
Yes, if
It
and
takes
else, that's it. Yeah.
Yeah. So if you write the code, it will give you the direct transitive closure output. So this is the latest trend to find the transitive closure. Or if you don't want to do this, you have to do this. Either way, it consumes some time, maybe some 10 minutes. So we know that if you have given you some 10 vertices, it will take you 10 minutes. So in order to complete within 5 minutes, we will give you some 5 or 6 vertices. That's it.
Actually, after spending 10 minutes also, there is a chance of error. There is a chance of missing one edge or like that.
That is what I said now. So there is, as the number of vertices increases, there will be a chance of error. So in order to decrease the chance of error, we will decrease the number of vertices.
Okay.
That's it. So it will be beneficial for you as well as for us. Both of us are happy. Okay. Yeah. Let's see quickly matrix multiplication. I hope many of you people know what matrix multiplication and how you compute. In order to
Yes,
bring
yes.
everyone to the same level, I will just quickly tell you how to find the matrix multiplication. So addition, you can see it from lecture. It is just the adding this particular value to this particular value, that will become. So add aij to bij to get the cij. So you watch the lecture, and addition is very easy. Multiplication is slightly difficult to understand in the very first sense, but even saying that, even addition multiplication is also not that bad. Okay, what you how to get. So these are the entries we discussed, right? These are the matrix. So matrix is nothing but n cross m arrays. So it is a two-dimensional array. So where one dimension contains rows and another dimension contains columns. So here you see this is a matrix of 3 rows and 3 columns, and even this is a matrix of 3 rows and 3 columns. In order to find the multiplication between two matrices, the number of columns of the first matrix should be equal to the number of columns of the second matrix. Then only you can perform matrix multiplication. So if that is different, you cannot perform this multiplication.
It's number of rows in the second matrix.
Yeah, in the second matrix, it's number of rows.
Number of
First,
rows.
did
First
I
matrix
said
number.
column?
Yeah.
Okay, sorry. In the first matrix, it should be the number of columns of the first matrix should be equal to the number of rows in the second matrix. Okay, so that means this must be equal to this, and this is how the multiplication goes. So in order to find the first row, first column, what I will do is I will take the first row of the first matrix and the first column of the second matrix, and I will multiply the first term to the first term, second term to the second term, and third term to the third term, and I will add all these three, and that will become the first row, first column element for the multiplied matrix. So this will be 11 times A11 plus 12 times A21 plus 13 times A30. So you see this particular 11 is multiplied with this A11. This 12 should be multiplied with this A21. This 13 should be multiplied with A31, and we will add all these three numbers to get the first row, first column element. So similarly, you do for the rest of the things also. So the second thing is first row, second column element will be first. You take the first row of the first matrix and the second column of the second matrix, and you multiply the first term to the first term, second term to the second term, third term to the third term. You add all. So that means A 11 times A12 plus 12 times A22 plus 13 times A3. So this will be the first row, second column. Similarly, you can find this. So this will be, you take the third row times, first row and third column. You multiply these two. Likewise, you can fill this. So this will be the, this is how the multiplication of true matrices will give us. This is the output of the multiplied matrix. Okay. Now, how this will relate to our graph theory? Why we studied this particular matrix multiplication in our graph theory? The idea is, if I have an adjacency matrix, so we know what is adjacency matrix means. Adjacency matrix is nothing but another way of representing a graph. So if I have an adjacency matrix like this, so I will denote it as A. Now I have a matrix A. I can compute A square, which is nothing but A times A. So I have to multiply matrix A with the same matrix A to get a new matrix A square. And this particular new matrix A square, in this particular A square, once I find it out, so if I find that out, that will be 0 1 1 0 0 0 0 1 0 1 0 1 0 0 0 0. So I should multiply it with 0 1 1 0 0 0 0 1 0 1 0 1 0 0 0 0. So if I multiply this, see, remember we have to multiply the first row, first column will be 0 times 0, 1 times 0, 1 times 0, and 0 times 0. So this will be 0 plus 0 plus 0 plus 0. So this will be 0. So this is how you have to find. Now the second element will be first row, second column element will be 0 times 1, 1 times 0, 1 times 1, and 0 times 0. So if you add all those things, you will get
1.
similarly 0 times 1, 1 times 0, 1 times 0, 0 times 0. This will be 0. 0, 1, 1. So now you see you are getting 0 plus 1 times 1, 1 plus 1
2.
times 1, 1
1.
plus 0.
0.
So
2.
now usually if you multiply this matrix, we are going to get the value as 2 here. Correct? So the first
Yes,
row,
sir.
fourth column element will be 2. But even though it is 2 or non-zero value, we are not worried. We are only worrying about, so in our graph theory, what we worry about is only the paths. So we don't need the weight of the path. We just worried about whether there is a path or not. So in order to worry whether there is a path or not, we actually use the Boolean values only. If it is 0, it will be 0. If it is any other number, we will put it as 1 only. So if it is 2 also, we will give it as 1. So I will tell you what this 1 states mean. So we will just replace the 2 with 1 only. So now the multiplied matrix will also have only either, all the entries will either be 0 or 1. So if you are getting 0, you keep 0 as it is. If you are getting any other value other than 0, then we will put the value as 1. So that is how we multiply it. So now 0 times 0, 0, 0, 0. So now what you have to do is you take the second row, first column, multiply each element and add all those elements, you get 0. So this will also be 0. So I will just quickly finish this. If you are quick enough, follow me. If you are confused, just try it out by your own. So 0, 0. So this will be 0. This will also be 0, 0. So correct me if I am going wrong. 0, 0, 1, 0, 0, 0, 0. Okay. So I will get a new matrix A square where there are again the entries are 0 and 1. We made it 0 and 1. So 1, any other number we made it 1. Now this particular matrix A square gives me the paths of length 2. So when I say length 2, that means by traveling 2 edges in between, each path has 2 edges. So this particular one tells me that, so if I have given vector numbers also as I, J, K, L. Let us say I, J, K. So I,
Sir,
J.
where the 2 number is gone? There
Hmm?
was 2. In a matrix,
In a
across it.
matrix,
2, there was 2 in first
there
row.
was,
There was 2 in first row.
yeah, there was 2 in first one. That is what I said. If you get any number other than 0, you just replace that number with 1.
Okay.
Okay. So this is 2. It is a non-zero entry. I just made it 1. That's it. That even that is 2 or 20 or 200, it doesn't give us anything. So it tells us that there is a path from I to L of length 2. So there is a path of length 2 from I to L. So that is what this one tells me. This one tells me there is a path of length 2 from I, vertex I to vertex J in the given graph. Similarly, if I find AQ, A cube can be found once you found
Sir,
A square. A square. Any doubt?
sir, how to find a to the power 1001?
A to the power
1001.
Okay, if your number of vertices is less than 1001, this will become just a zero matrix. Got it? Or simply you just multiply A 1000 times if you are interested. Okay. So for A cube, I can actually take A square multiplied with A. So A square multiplied with A. I have A square as 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. And A is 0, 1, 1, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0. So if you product this, you will get something. I hope this will be. Just check this, because I will not have any path of length 3 in the given graph. So how long we proceed? So do I have to compute this? How long? How many matrices do I have compute? Should I compute like this? Should I have to go till a power 1001, or is there any upper bound to this value? To this?
Actually, once you hit zeros, then you don't have to do anything further, right?
Yes. Yes.
Yeah. Correct. So when will we get all zeros? So can I 100% with 100% guarantee? Can I say some a to the power something will always be zero matrix? So
Yes,
is
sir.
there any upper bound?
If there is
N
no
minus
path,
1. N minus 1.
Yeah, n minus 1 is correct.
N
But why? Why n minus 1?
Number of edges are n minus 1. So after that we will get 0 only.
Number of edges are n minus
Number
1?
of vertex is 4. Just now sir said that if the number of vertex is 4, then we just have to calculate till.
Why? So that is my question. So there will be an upper bound for sure, and the upper bound is also n minus 1. It is also true.
A maximum length of the path maximum is n minus 1, right?
Correct. So that is the correct. So in a given graph, if you have n vertices with you, the maximum path length can be n minus 1 only. You cannot have path of length n or n plus 1 or something. If you are saying path of n plus 1, that means that is not path. That will be a walk. Okay, that will become a walk. So n minus 1, the maximum path in an n vertex graph I can have is n minus 1. So
sir, first row, fourth column when we multiply. First row, fourth column.
First column?
First row, fourth column. It will go give 1.
Yeah. This will be 1. Correct. So a to the power 4. Yeah. A to the power 4 will give me 0. So there will not be any path of length 4. I should go till a cube. Okay. So because my n is 4 here, I should go till n minus 1. That means I should go till 3. So let us check by drawing the graph also. So this is how this a cube now gives me paths of length 3. So this is telling me that there is a path of length 3 from I to L. Let us check, is there a path of length 3 or not? Okay, let me check. Let us draw this. We have the adjacency matrix with us, right? We can draw the graph. So vertex I, vertex J, vertex K, and vertex L. Now I to J, there is a directed edge.
I to K.
I to K, there is a directed edge. And J to L, there is a directed edge. K to J. and K to L. Yeah. So yeah, from this adjacency matrix A, this is the graph we get. This is the graph that represents this adjacency matrix also. We found A square, right? A square gives me only three. There are only three paths which are having length 2. So what are the paths? I to J. Okay. I to J, there is a path of length 2. Yes, correct. I to J, there is a path of length 2. I to L, there is a path of length 2. So this is one path and this is another path. So you see, that is why we got 2 here. So the 2 tells me that there are 2 paths which are of length 2. But we don't need to worry how many number of paths of length 2 are there. We are worrying about whether there is a path of length 2 or not. That's it. That is why we replace the 2 with 1. So there are 2 different paths, I to K, K to L, I to J, J to L. There are 2 different paths of length 2 from I to L. But anyway, we can conclude that there is a path of length 2 from I to L from here also. Right? And there is one more path which are of length 2, K to L. K to L is also a path of length. Yeah, correct. So A square graph gave me the paths of length 2, and also when you verify it with your graph, it is correct. All right. Now A cube, we got only one path of length 3, and that is from I to
I to L.
Is there a path of length 3 from I to L?
Yes, I to K, K to J, and K, J to L.
Correct. So I to J, I to K, K to J, J to L is a path of length 3. So yeah, correct. And this is the only path that has length 3. And if you compute A to the power 4, so you see A to the power 4 is nothing but you can use A cube times A or A square times A square. Anything gives me A to the power 4. So A cube, I have only one entry, non-zero entry. Everything else is 0. A is something like this. So if I compute this, I will get everything zeros.
Yes.
Correct. So once you get everything zeros, that tells you that there are no paths of length 4 in your graph, and that is correct. See, if you have only 4 vertices with you, the maximum path I can have is of length 3. I cannot have a path of length 4.
Sir,
Hmm.
so it will just change the direction of KL, the edge KL, then we'll get a path of length 4, right? So can we still generalize this statement that
If I KL, is it?
yes, sir.
If I do it like this, yeah, then there will be a path of length 4. Yeah.
So a raised to 4 will not be 0 in that case. That won't be a 0 matrix, right?
Okay, just a second.
But then the other calculations, but the other calculations might affect that, right?
No, this is not a path, right? Is this a path?
Then this is
I to K, K to J, J to L, L to K. Is this a path or walk?
Not your path. K, what is this you are repeating? No?
Correct.
It's not your path.
So see here, your vertex is being repeated.
So this is a walk.
This will be a walk. And we are least bothered about walks. We are only worried about paths.
Okay.
Okay?
Yeah.
Yeah. So yeah, this is about transitive closure. Matrix multiplication and how we link matrix multiplication with the transitive closure. Now the thing is, once you know paths of length 1, length 2, length 3, it will obviously give you there is a path, whether it can be length 2 or 3 or 4 or n minus 1, whatever it may be. If there is a path, then I can compute the transitive closure. From these matrices also, you can actually able to compute the transitive closure. Okay, now let's quickly finish this problem statement. Yeah. So after this, we will move to weighted edges. Okay, I just missed that topic. So till now we have seen uh, graphs which are only directed and undirected. Until now we didn't impose any weight to particular edge. From now on, what happens is, what if there are some weights on edges? So that, but now what it tells us that is, before that every edge is treated equally. So in this particular graph, every edge is treated equally. That means weight of every edge is equal. So it means even if you travel from I to j, it takes same time, or these weights can actually refer to time or kilometer distance or money, whatever it may be. But whatever it may be, in this unweighted graphs, what it tells us that is weight of every edge is equal. That is what it, till now we didn't study it, because in this particular cases weights of every edge is equal. Now what if weights are different? Okay, if I give some weight 2 to this and some weight 3 to this, so now this particular edge from I to j is different from this particular edge I to k in terms of weights or distance also. That is where that is what this weighted edges concepts come into play. Even in the real scenarios or real cases also, most of the graphs we have weighted graphs only. We least bother about unweighted graphs, because not always every edge will have same weight, or not every time you work in the same pace, or not every time you reach from one district or one place to another place in one particular way, right? So in real life also, these edges corresponds to some particular uh, thing, and that particular thing can have weight, whether it may be distance, or whether it can be time, or whether it can be money related thing. I should give 200 rupees to j, and it might be different that I should give some 300 rupees to k. So not every time I gives same amount to everyone. So these kind of things. So if I have associated one more number to every edge in my graph, then those graphs are called weighted graphs. So weighted graphs are nothing but giving weights or associating one number to every edge in the given graph. So I associate a number to every edge in the graph, and I call this number as weight. So these type of graphs are called weighted graphs. Okay. When I have weighted graphs, now till now shortest path means we talk about only in terms of edges. Now when I have a weighted graph with me, now there are two different cases. I should specifically mention, if I ask you the shortest path, I should specifically mention in which terms, whether it is number of edges or whether it is the weight of edges. Okay, now we have two different paths, two different ways to find the shortest paths. So one way we can ask you find the shortest path in terms of weights of the edges. So there you have to find the minimum weight, or we can ask you find the shortest path in terms of edges. So when I talk about in terms of edges, you should count the number of edges. So if the number of edges are more, then that will be the longest. If the number of edges are less, then that will be the shortest. And this shortest, if the number of edges is small, is less, this may not correspond to the shortest path when it comes to the weighted graphs. So when you add the weights of all the edges, so that particular weight should be very less, and we will consider that particular path as the shortest path. Yeah.
Excuse
So,
me, sir.
so for today's
Uh,
session, sorry to interrupt you in between. We have a back-to-back session for the next class also. So, are we covering more topics today, or are we
When is your next session?
now
6,
we'll
just now.
it
Just now
started, I
it's
think.
already
Okay.
started.
CT.
Then in that case, we will cover algorithms tomorrow.
Tomorrow,
Yes,
yes.
Sir,
That's good.
can you send these notes also?
Yeah, maybe I will add this tomorrow evening after completing everything.
Yeah,
So
okay,
I
sir.
don't
No.
think you will go through. You don't have that much time, I guess. Now you have to attend one
So
more
are you
session.
going to stop it now, sir?
Yeah, we will stop it now. We will stop it for
Yeah,
today.
that'll
And
be great.
tomorrow we will start discussing each of the algorithms.
Yeah, thank you. And one more issue, sir. On 24th, there is a overlap between CT and no, yes, yes, with CT and maths. Both are in the same time.
Is it?
Yeah.
3:32.
Yes.
No, 4, I guess.
No, oh yeah, sir.
7 to 9, sir.
Yeah, same
This is
time.
7 to 9. Even CT is at 7 to 9, is it?
Yeah,
Yeah,
same
Yes,
time,
yeah.
sir.
same time.
So then we will move one session to 5 to 7.
Can't you put this session in the morning, if you don't mind?
See, some people will ask at morning and some people will ask at evening. We don't know.
Please try
Because
to keep at least 1 hour gap between two sessions
Yeah,
because it
that
will
we
exactly.
take
will.
a long time.
Yeah, we will plan.
Otherwise, it's be like,
At
Okay,
this
sure.
time,
We
so
will.
with us now, we will have all these algorithms, so it may go on beyond 3 hours. So 3 hours also, algorithms are difficult.
Sure,
It
sure,
takes
sure.
time for the students to
but
understand. So
anyhow, you're going to come tomorrow also, no?
Yeah,
So,
tomorrow
yeah.
we will see whether me or Vicky or someone
Tomorrow
else.
also back to back there is
No,
class.
tomorrow only maths.
No, there is this thing
nothing,
also.
nothing. Dipti tomorrow, nothing, only maths.
Okay, maybe we will
Solve
move
with us
this
at later
particular
date.
session to 4 to 6. Okay.
and sir, just one request, because we were struggling from last few session when Vicky also took the session. No, we were not able to log into Zoom. So today I have to call to literally the online number and tell them to just allow us to log in into Zoom, because watching into YouTube doesn't make any sense.
Right.
We
We
cannot ask
understand.
any doubts.
There'll be no
That was
interaction.
Yeah, there's
Basically.
no interaction, so we lose the motivation to join the sessions then.
correct. That was an mistake. By mistake, it happened.
Yeah,
Okay, it
yeah.
was not intentional, but it has
No,
happened
because
by mistake.
sometime the message got to us that it was not for us, it was for diploma students, so we also got confused.
No. It
So
was
that kind of confusion it creates. So thank you very much.
sure.
Yeah.
Okay. No worries. From next time, it won't happen.
No issues, sir. Thank you. Thank you.
Yeah. Okay. Then we will stop here and we will meet you tomorrow. We will meet tomorrow.
Because I have one doubt, can you clear?
Yeah. I can.
No, actually, matching part is not clear for me. Question number 6 in the graded assignment. I don't know matching. I was unable to get it till now. I don't know.
Just let me open that.
Question number 6.
Thank you, sir, for the patience.
Yeah. Thanks everyone. Have a good day.
Thank you, sir.
Thanks.
Thank you.
Thank you, sir.
Thank you, sir.
Okay. Question number
Question
6.
number
is it?
6. Yeah, graded assignment. Question number 6.
Which of the following graphs satisfies?
Yeah, I got 3 and 4 for the first two options, right? Those first option is vertex cover, and second is coloring. I easily did it, but matching part, I'm unable to get it. What it means actually, cardinality of PMG.
That means PMG denotes the perfect matching. Perfect matching means we discussed, right? Matching it is a subset of edges, and in
Maximal subset you told.
Maximal subset we said, but when it comes to perfect matching, when I say word perfect, that means every vertex need to be covered.
Yes.
Correct. So if you see here, if I take in my matching, if I take this edge, okay, I cannot take this edge.
Yes.
So I can take this edge.
Yes.
Then if I take this edge, I cannot take this edge.
Yes.
I should take this edge.
Yes.
So I can take this edge, and this edge, right? 3 edges, And also these 3 edges covers all the 6 vertices.
Yes.
So if it is covering like that, then it will be a perfect matching.
So a perfect matching should cover all the vertices.
All the vertices. That's it.
Okay, that's where I missed.
Yeah. So you will get the solution. Okay. Maybe like today evening or at most tomorrow morning.
Okay. Thank you.
Yeah. Thanks. And thanks a lot, guys.
Thank you so much.
Yeah.
Thank you.
Have a
Thank you, sir.
Sir,
Hmm?
so can I have a small doubt regarding one doubt what final grading which will be getting for each?
Okay. Can I ask you one doubt?
Yeah,
Before
sure.
this doubt? Are you not attending CT session?
No, sir, I have only math.
Okay, you are only. Okay. Then yeah. What is the
Yes,
doubt
sir.
in
So
grading?
yeah. Sorry.
Yeah, you can ask what is the doubt you
Yeah.
have.
So if we have let's suppose there's a case the final percentage out of considering all the quizzes and the end-term exam, we are getting supposedly 79%. Okay. And so I just want to know how since we are getting all the results in the form of percentage, so how that bonus mark is getting help in increasing the grade, because if we are getting 79%, that means we are getting B grade, right? So how it's helping us in that improving the grade?
So in that 79, are you including this bonus marks or?
No, excluding bonus marks.
Excluding bonus marks, right? Now
Yeah.
you are at 79. So
Yeah.
let's say you have some bonus marks of 5 marks.
Okay.
Okay. 5%. You have 5% of bonus marks. Okay.
Okay.
So if I add that, you will be going to 84%.
Oh, so that 5 marks is 5%.
Yeah, 5. More or less it will be same. 5 marks means 5%.
Okay. Thank you, sir.
If you have that completely,
Mm-hmm.
then we will add that 5%, make it 84 and give you A.
Okay.
But the thing is, if you have 74, okay, even though if I add you 5%, it will
It's
sum up to 79. So your grade won't affect.
Yeah, got it.
So bonus marks is not effective at that particular point.
Got it, sir.
Okay.
Thank you.
Yeah. Thanks. So yeah, thanks a lot and bye all. Meet you in the next session.
Thank you very much, sir. Thank you very much.